In the last decade, location-based services have received significant interest driven by numerous applications in domains such as asset monitoring, access control, indoor navigation, and tracking. According to Savary, localization-based systems should be cost-efficient, energy efficient, have a wide reception range, high localization accuracy, low latency, and a high scalability in order to have a wide-scale adoption. A sought-after feature in many applications is the fully passive operation of the tracking device. As no local power source such as a battery is required, maintenance and device costs can be reduced while flexibility and lifetime can be increased. For fully passive devices, RFID has been grown into the key technology of choice. However, the accuracy of the RFID localization systems based on the received signal strength indicators is limited in the order of meters and is strongly affected by the multipath effects and tag orientation. Phase of arrival methods typically show a better localization accuracy, but currently suffer from two main issues: ambiguity due to the phase periodicity and phase offset. In this paper, we want to attribute to the energy-neutral device positioning research and pose the question if hybrid RF acoustic signals can point them out. Hybrid RF and acoustic positioning combines the best of both worlds. On the RF side, one of the most promising technologies that meets many quality metrics for indoor positioning is ultra-wideband. It has a high resolution in time, large resistance against multipath fading, but has limited spectral power density. This makes it insufficient to power ultra-wideband tags at useful distances. Due to their low propagation speed, acoustic signals can have a large positioning accuracy with low processing power. In contrast to ultra-wideband, acoustic signals are susceptible to multipath interference. We will implement a hybrid RF acoustic time difference of arrival system where the RF link is used for both communications and as a time reference. In order to meet the power requirements of the hybrid RF acoustic tag without batteries, two main techniques can be exploited: RF backscattering and energy harvesting. The first one is used for indoor localization purposes. After that, the position is used to beamform the energy to the energy-neutral device. Hi, we are Bert Cox, Chesney Builen, Liesbeth van der Per and Lieve de Strijker from the Dramco Research Group at the KU Leuven in Belgium. This presentation is split up into 4 parts. In hybrid RF acoustic positioning, we explain the positioning system used in this research. The energy constraints and beamforming are talked over in the energy neutral device section. Next, the measurements are discussed, and we finish with a conclusion and future work. We first start with the hybrid RF and acoustic positioning. The main question in this section is, how can we position the mobile node? For this, we extend previous research on the topic of hybrid RF acoustic positioning based on the time difference of arrival principle of the two signals. Current setup is as follows. Powered beacon is equipped with both an RF transmit antenna and a speaker. The mobile nodes are spread across the room and can move freely. They are equipped with a low-power MEMS microphone and an antenna. Positioning is done in 4 steps. In the first step, an audio signal with a certain duration is broadcasted by the beacon. The mobile nodes receive a transformed and delayed version of this audio signal depending on the distance to the beacon. In this figure, mobile node 1 is closer to the beacon than mobile node 2 and Z. The next step is to simultaneously awake the mobile nodes through an RF pulse. During their awake time, they will sample a certain part of the delayed distorted audio broadcast. In the third step, the collected data is backscattered over RF. And lastly, a bit-based correlation is searched between the transmitter and the received audio signal. Pulse compression shows a distinct maximum, and the inter-beacon and mobile node distance can be calculated. Trilateration can be performed to find the position when 3 or more distances are combined. The internal schematic of the mobile node consists of a MEMS microphone, an amplifier to enhance the received audio signal, a comparator to quantize the audio signal. It is this quantized signal that steers a multiplexer, switching between 2 local oscillators. These local oscillators are used for frequency shift keying and drive an RF switch loading the antenna with two different impedances, resulting in the absorption or reflection of the received RF signal. The bottom part of the figure is used for backscattering. With this, the tag is able to transmit information by modulating the incident electromagnetic fields from an external source to its antenna impedance. This lowers the energy efficiency for RF communications by multiple orders of magnitude. Using the local oscillators for frequency shift keying eliminates self-interference present when using amplitude shift keying. The next section in this presentation is the energy neutral device. Now that we have the position of the mobile node, we need to power it. But how much power does it need? For this, we look at the hardware used at the mobile node. The table shows the power consumption for every component and their turn-on time. It shows that the ultrasonic MEMS microphone has a relatively high power consumption and a large turn-on time. A split startup reduces the turn-on energy drastically, and with an awake time of 1 millisecond, the total power is calculated to be 11.7 microjoule. But how can we transfer that much energy? To answer this question, we look at the possibility of beamforming and its energy transmit capabilities. What did we do? At the transmit side, an antenna array is used to increase the directionality and thus power towards the mobile node. Why? Beamforming is adopted as the RF interface is already present. With beamforming, we limit the interference and lower the transmit power at the beacon. We want to note that according to the ETSI regulations, the maximum effective isotropic radiated power in the European 868 MHz band is limited to 27 dBm. It doesn't matter if you use an omnidirectional dipole or an antenna array, the maximum beamform power is the same 27 dBm. How? As mentioned before, the beamforming is performed into two stages. A pre-charged phase where the energy buffer of the mobile node is charged until there is enough energy present to perform the next phase, namely the ranging. After this phase, the position is used and the beamform is adapted in a way that the maximum gain points towards the new known location. At the mobile node side, we use the AEM4940 chipset of EPs. This consists of an antenna, a matching network, an energy harvesting chip with boost converter and LDO in it, and an external energy buffer. In this paper, a dipole antenna with a 2.15 dB gain and a storage capacitor are chosen. The value of this capacitor depends on the required energy, the LDO efficiency, the over-discharge voltage, and the charge-ready voltage. With the previously calculated required energy, a minimum capacitance of 68 microfarads is chosen. Simulations show the charge time in function of the Friese transmission formula and the energy harvesting efficiency. Two scenarios are plotted, the initial and the update charge time. This first time is the time it takes for the energy harvester to charge the capacitor from 0 voltage to the charge-ready voltage. This scenario occurs when a tag has not been powered for a long time. The second scenario shows the update charge time. This is the time it takes for the energy harvester to charge the capacitor from the lower over-discharge voltage to the charge-ready voltage. This occurs when a ranging measurement has already taken place. The charging distance in this latter scenario is larger, up to 7 meters. For lower distances, the charge time is decreased significantly. The next section, we test the hypothesis in a real-life environment. Measurements are performed in a non-ideal situation to match the real-life applications. The energy harvesting module is positioned on 8 different distances, and a total of 10 power measurements are performed on each point. The average of those 10 measurements are plotted in blue for the initial charge method. When comparing the results with the simulations, a larger charge time is obtained at every distance. This is due to losses in the transmit and receive antenna and cables. of not being in free space, and of a lower efficiency of the energy harvesting chip than calculated. For distances larger than 4.5 meters, not enough energy can be captured to charge the capacitor. In this last section, we will answer the main question of this research. Now, can hybrid RF acoustics point them out? Well, the answer is yes, but there are some limitations when looking at the initial charge plots. The maximum distance is 4.5 meters, which is lower than simulations, and the update rate for the initial charging is 20 seconds at 3 meters. This means that the hybrid RF acoustic positioning system is ideal for applications with an update rate of minutes rather than seconds, but they can opt for centimeter accuracy. Examples can be found for packages in retail or monitoring equipment in hospitals. Note that the worst-case scenario results are presented here for situations where the energy buffer is completely drained. In case of the update scenario, both distance and charge time will be enhanced. Now, what is the cause of these limitations? Well, they are coming from regulations. As stated before, the maximum effective isotropic radiated power in the European 868 MHz frequency band is 27 dBm. In addition, there is a 10% duty cycle regulation, which lowers the initial charge update rate even more, up until minutes. The research performed in this paper is far from done, and in the future we want to extend this with the following points. For increased energy transfer, a dual band RF antenna can be used to harvest energy into two different RF bands. Current localization and energy harvesting measurements were performed separately. In the future, we will perform them both at the same time. To increase the update rate even more, a combination of different energy harvesting methods can be used, and as omnidirectional power transfer can reach more mobile nodes at the same time, the influence on the multipath effects have to be investigated. We want to thank you for listening to our presentation. If you have a question, you can pose it through the conference virtual portal or by sending them through mail to bert.cox@kuleuven.be. If you're interested in the research we perform, you can visit our research group website on www.dramco.be. Thank you.